All right, picking up in part C, I said that I was going to show you how to use the shortcut on that last example we did, and here it is. If we designate, say, the potassium permanganate to be reactant A and the oxalic acid to be reactant B, which you might as well do since that's the order in which you encounter them, so it makes sense to go A, B. And notice I wrote it down so I wouldn't forget. We can use our equation, MAVA over little a equals MBVB over little b. And again, rearranging it to find MB, that is the molarity of substance B, we end up with the equation MAVA times little b over little a times VB. And you can just plug the numbers in and you don't even have to change the liters. So MA, that is the molarity of the permanganate, was given in the problem as 0.09113. So write that in. The volume of the permanganate was 23.24 milliliters. B is the coefficient of the other stuff, which is the oxalic acid, which is 5. And then on the bottom, we've got A, little a, that is, which is the coefficient of the permanganate in the equation, which is 2, times the volume of B, which again is the oxalic acid, and that was 20 exactly. So when you multiply all that out, you get, guess what? 0.2647, the same we got doing the 3 steps. So again, if you want to use the shortcut, you're welcome to do that. But remember that you can only use the shortcut if the two substances you're interested in are both aqueous. That is, they both involve volumes and molarities. If either of them is a solid, for instance, then you're out of luck. Got to use the 3 separate steps. This brings us very close to gravimetric analysis, which is the topic of the next section, or the next section of this section anyway, subsection, I guess. Gravimetric analysis is an analysis where you can find out how much of something is present in a sample if you can get the part you're interested in to react with something that will cause it to precipitate out of solution. And then you can filter out the precipitate, the solid, and weigh it and sort of back calculate to how much of the original substance must have been in the sample to begin with. So essentially, you're analyzing a component that's soluble by putting it through a reaction that produces a precipitate. You're reacting it with something that makes it not soluble. The precipitate is then collected and weighed, collected by filtration usually, and the amount of precipitate is related stoichiometrically to the amount of the original compound present. So that's what we're doing here. If you have 1.1324 grams of an unknown sample containing soluble chloride compounds, so we don't know what it is. We know that they're soluble chloride compound or compounds. So it could be sodium chloride, potassium chloride, calcium chloride, or even a combination of those. But basically, chloride compounds that are soluble in water. And we want to find out what is the percent chloride in this sample. How much of that sample is made up of chloride ions? Well, what you can do is react that sample with something that will cause the chloride ions to precipitate out and basically filter out that solid and weigh it and relate it to the amount of chloride that was originally present. In this case, we're going to react the chlorides by adding silver nitrate to them. Silver nitrate, when combined with chloride ions, will undergo it's essentially a double displacement reaction, although it looks like a single displacement reaction the way I've written it, because the silver and chloride ions will grab onto each other and not let go. Silver chloride is not soluble in water. And so that falls out of solution as a precipitate, and we can filter it out and weigh it. So if this amount of the unknown sample produces 1.0881 grams of silver chloride solid, what was the percent chloride in the original sample? So essentially what you're going to have to do is take the amount of silver chloride you get as a precipitate and find out how many moles of that you have, and find out from that how many moles of chloride you have, and then find out what the mass of chloride was of that many moles is, and then you can take that as a percentage of the mass of the whole sample. So again, we've got mass of silver chloride to moles of silver chloride. Whenever you're doing a stoichiometry problem, that's always your first step. If you're given a mass, find the moles. In order to go from mass to number of moles, of course, you divide by the molar mass or multiply by 1 over the molar mass. In the case of silver chloride, the molar mass is 143.5 grams per mole. So if you want to divide by that, you can multiply by 1 over 143.5. That way, grams of silver chloride clearly cancel out, and we end up with moles of silver chloride as the unit, which is what we want. And the number would be 1.0881 times 1 divided by 143.5, which is 0.007583. That's how many moles of silver chloride we precipitate out of that solution. The number of moles of silver chloride, from that we need to find how many moles of chloride ion there were. And well, obviously there's only one chloride. Okay, now that I've taken care of that, there's only one chloride for every AgCl, so that means there's only 1 mole of chloride ion for every 1 mole of silver chloride. So that's times 1 over 1. Moles of silver chloride obviously cancel out, and you get the same number again as moles of chloride ion. And we now need to find the mass of chloride ion. That may seem difficult, but we can assume that the mass of a chloride ion is the same as the mass of a chlorine atom. And that's because the mass of the extra electron that makes it a chloride ion is minuscule compared to the mass of the atom. 1/1800th of an atomic mass unit. So for all practical purposes, a Cl- ion weighs the same as a Cl atom. So the number of moles of chloride ion times the mass of a mole of chloride ions, which is the same as the mass of a mole of chlorine atoms, 35.5, tells us that there were 0.2692 grams of chloride ion in that sample. And so now if we want the mass of chloride ion, or the percentage would be the mass of chloride ion divided by the mass of the sample. In other words, the part you're interested in divided by the whole thing times 100. That's 0.2692 divided by 1.1324 times 100. That's 23.77%. So not too hard. The combustion analysis. Combustion analysis is also a type of gravimetric analysis, only in this case, you're weighing how much stuff leaves the reaction vessel. Because when you burn things, you usually produce at least one product that's a gas. Combustion analysis is done most often for organic compounds, which contain carbon and hydrogen. And usually what happens is that the carbon will become carbon dioxide and the hydrogen will become water. Depending on how it's done, it could be liquid water or it could be water vapor, which is gas. And from the amount of the products that are produced, you can actually tell what the percentages of carbon and hydrogen were in the original sample. So again, from the you basically you take a weighed sample of an organic compound which contains carbon, hydrogen, maybe oxygen, and completely combust it. You have to combust it at a really high temperature with a lot of oxygen present to make sure that it burns completely. All of the carbon in the sample should become carbon dioxide. All of the hydrogen in the sample should become water. And you can, depending on how you conduct the experiment, you can perhaps collect and separate the carbon dioxide in the water. And from that, again, from the mass of the carbon dioxide, you can get the mass of the carbon in the original sample, which tells you the percent carbon. And from the mass of the water, you can get the mass of the hydrogen in the original sample, which gives you the percent hydrogen. And then 100% minus the total of those percentages will give you the percent of oxygen, if there was any. And so you can essentially find the empirical formula from the percents. So you can actually use a combustion analysis to find the empirical formulas for the compound. Okay, an example would be, say, what if 0.00215 grams of a sample of polystyrene, which is the plastic that's abbreviated as PS. It's a fairly somewhat rigid plastic that's used a lot in things like trays for cookies and that kind of thing. If you look at the recycling abbreviation on those, it usually ends up being PS, which is polystyrene. And it's a polymer of carbon and hydrogen, no oxygen present. If it produces 0.00726 grams of carbon dioxide and 0.00148 grams of water in a combustion analysis, what is the empirical formula of polystyrene? Okay, so that's what we're looking for here. So essentially what we're going to do first is find out the percentages, or actually, we don't even have to find percentages in this case because we have the information of masses, which will lead us to moles. And so we can just use the moles to find out the empirical formula. Our equation can be represented like this, CXHY. We don't know what X and Y are. Those are the subscripts for carbon and hydrogen in polystyrene. We don't know what they are at this point. But when combined with oxygen, they should produce a certain number of moles of CO2, which should be X number of moles. So if X is 2, then you should get 2 CO2s out because CO2 is where all the carbon goes. And Y over 2 moles of H2O. Because say if Y is 2, then you should get 1 mole of H2O out of it because each H2O contains 2 hydrogens. So that's why it's Y over 2. But that doesn't really matter. It's just sort of giving you a reaction to look at. The number of moles of CO2 can be converted to the moles of carbon, or sorry, the mass of CO2. Mass of CO2 can be converted to the number of moles of carbon by first converting to moles of CO2 and then to moles of carbon. So if you have 0.00726 grams of CO2 and each mole has a mass of 44 grams, that means you have a certain number of moles of CO2. And since there's 1 carbon in each CO2, the moles of carbon would be the same as moles of CO2. So it's 1 mole carbon over 1 mole CO2. And that tells us that we had 0.000165 moles of carbon in that original sample. For hydrogen, again, we're actually converting from mass of H2O to number of moles of hydrogen. So if you take the mass of H2O and divide by the molar mass of H2O, you'll get the moles of H2O. And there's 2 moles of hydrogen for every mole of H2O. So you take the moles of H2O and multiply by 2 over 1, and we get 0.00164 moles of hydrogen, the element. So the empirical formula will involve the subscripts for the carbon and the hydrogen. And so if you take the number of moles of carbon and the number of moles of hydrogen from what we got above here, you notice they're almost exactly the same. So you have a feeling this might come out to be a 1-to-1 ratio. And indeed it is, because we take 0.000165 moles for the carbon and 0.000164 moles for the hydrogen, and divide them both by whichever number is smaller. That would be the 0.000164. So hydrogen comes out to be exactly 1, and carbon comes out to be 1.006, which is equivalent to 1, close enough. And so the empirical formula for polystyrene is CH. That's the empirical formula. Remember, the lowest whole number ratio of carbons to hydrogens in the molecule. The actual formula, well, this is a polymer. So a polymer is like a chain made up of individual links. The individual links are known as monomers. And so the actual formula for the polystyrene would really depend on how many monomers are strung together in that particular sample. So we don't really have any way of knowing that. You'd have to do mass spectrometry on it or something like that to find that out. But the empirical formula anyway is CH. So however many carbons you have, you got the same number of hydrogens. All right, that brings us finally to the end of this chapter. That's the end of chapter 4. Hopefully you've been keeping up with the homework. And I would like the homework to be due by the end of this week, so by Friday, midnight Friday. And also very soon we'll have to have another quiz, which would be on chapters 3 and maybe something from chapter 4. But I will let you know as the week goes on about that. So anyway, I'm not going to start chapter 5 yet because we don't really have that much time left in this segment of the lecture. And I went over in the first 2 segments anyway, so this will compensate. So I will see you next time.